Yeah, so yeah, welcome once again. So we'll continue from where we ended previously. So far we've been looking at the differential equation, and we are still working on differential equation. If you can recall, in our first parts of looking at differential equation, we made mention of linear differential equation and non-linear differential equation. So far, all the examples we have been working on has been on a linear differential equation. So now we have a non-linear differential equation. How do we go about it? So just consider a first degree linear differential equation we want to solve. The most important thing is reducing a non-linear differential equation to a linear differential equation by means of an appropriate transformation. In this transformation is as you see in equation 16, in which the coefficients of the derivative of y is a linear function of x and no other x appears anywhere again. Yeah, so no other x appears anywhere again. So with the equation 16 can be expressed as a linear differential equation with x as a dependent variable and y as an independent variable. And to be able to do that, we multiply through the transformation by dy dx to obtain this form, or that form as you see here. So this is then a linear differential equation of x as a function of the independent variable y. So for what we're doing, you were normally saying y as a function of x, but today it has been a slight difference where we have x, which is a function of what? Y. So let's take this differential equation to form. I hope when I ask you to describe this differential equation, you'll be able to do that. So one thing you realize that this differential equation is what? It's a nonlinear differential equation. So we reduce it to a linear differential form by multiplying through by dy dx. So we multiply through by what? Dy dx. This is what you have. Okay. So if you solve for this, you arrive at that. So we want to express it in a standard form. So you just divide through by y from here. If you express in a standard form, this is our standard form of the linear differential equation we have here. You realize that in our previous lesson we had p of x, y equal to k of x here. But this, you realize that this is what? A function of y. This is also what? A function of y. So finding the integrating factor changes a lot. And in the previous statement I made that x is a function of y, you could also see that here as well. So now let's find the integrating factor with respect to what? Y. There is a constant. If you integrate this 1 over y, you are getting ln y. So we can write the whole of this in this form, which will give us y cubed. Now that you know your integrating factor, you can multiply through by this. Then you take your time, solve, and this is what our final answer. So this becomes our general solution. So the previous nonlinear differential equation we reduced to a linear form. Very good. So I urge you to go through that. So if you have a linear differential equation of a higher order as well, so this is a linear differential equation, we are saying that if we equate this differential equation to 0, then it's called a homogeneous differential equation. If it's not equal to 0, then that's we call a non-homogeneous differential equation. So if I have a homogeneous differential equation, I can find the solution to the homogeneous differential equation, which we call the complementary function. And then that's of the solution to the non-homogeneous differential equation we are calling what? Particular what? Integral. So let's look at a homogeneous differential equation. So this is a homogeneous differential equation because it's what? Equal to 0. So we take a second order homogeneous differential equation to solve. So if I have a second order homogeneous differential equation, we are saying we can write y, the solution in terms of as this. So with this linear differential equation, wherever I see where I want to substitute what r there. So I want to express this in a form of this equation. I don't know if you recall, this looks like what's the quadratic equation, or what's normally you call the characteristic what equation. So if I have a characteristic equation, then what do? I need to find the roots of the characteristic equation, which is what r in this equation. So we would like to find r and then find the solution. So we are going, there are three cases to that, and the first case is if the roots, the r we are looking for, they are real and distinct. So real as in real numbers, and distinct, they are not of equal values around in R2. Then I can write my general solution in this form. But the second case is when they are real and identical, that is R1 is equal to R2, then this becomes a general solution of the differential equation. So I hope you can see the difference with the case 1 and case 2. Don't mess it out. So with the x here. The third case is when the roots are not real. If they are not real, it means that they are what? Complex conjugates. So I have r to be equal to what? This. If it's equal to this, then our general solution is of this form, this exponential form. Or normally, or however in practice, we prefer to work with real functions instead of working with, complex exponential functions. So we normally use the Euler's formula. So if you use the Euler formula and you work around it, you arrive at this general solution as well. So it's either this solution or that solution. So let's take an example. So you realize that this differential equation can be expressed as r squared plus 2r plus 1. If you find the roots of this quadratic equation, it's what? 1. So you realize that r1 is equal to minus 1, r2 is also equal to minus 1. That is the case of what? This case, roots, the roots are real and what's identical. So we write the general solution in this form. And that is what we have here. If you look at the second example, you realize that writing a quadratic equation, the roots are going to give you minus 1 plus or minus 2i. That is the complex conjugates. So I just use the complex conjugates here, the solution here to the Euler formula to solve. So I have alpha here, alpha is minus 1, beta is what? Minus 2. The third example is with this differential equation. Okay, so let's write the quadratic equation. If you write the quadratic equation, what are we getting? R squared plus r minus 6 equal to 0. So that is what you have, equal to 0. So you realize that r it's equal to r1 will give you 2, r2 will also give you what? Minus 3. So we can write the general solution. This can be compared to case what? 1, where the general solution was of this form. So our general solution for example 3 will be equal to this. I urge you to write your own differential equation, a homogeneous type, then solve going through what we just did. Now continue practicing. As I say, practicing makes what as what perfect. Thank you for today's lesson. As you know, we are not in normal times, so I urge you all to stay home and stay safe. Study as well.